Hi everyone, welcome to this tutorial on differentiation using first principles. The purpose of this tutorial is to show you where the first principles formula comes from and also how to use the formula correctly. If we're going to look at where the first principles formula comes from, we need to first of all start with the following diagram below. If you look at this particular diagram, you will see that we have a secant PQ drawn to the curve f of x below. So here we have the curve f of x. We don't know the rule for the curve, so we're just giving it that name, f of x. And on the curve we have 2 points. We have the point P here and the point Q. And you can see in blue there we have a straight line joining the points P and Q, which we know is the secant. You already know that a secant to a curve is any straight line joining 2 points on the curve. So here we have the secant PQ. First of all, let's look at the coordinates of point P. If we look at point P here, we have the x coordinate down here, which we will just call x. We don't know what exact value this x value has. It could be 1, 3 or 5, any value whatsoever, but we just call it x here. The y coordinate of point P is found by substituting x into the function. So the y coordinate of point P here will be equal to f of x here. So therefore we say that the coordinates of point P are x and f of x. Now let's consider the coordinates of point Q. Once again, if we look at the x coordinate of Q, we can see that its x coordinate down here is x plus h. Now this coordinate here is derived from the x coordinate of P here. Here we have x, and we have this horizontal distance here added onto x to give us the x coordinate over here. Now this distance we don't know, so we're just going to call it h. So therefore this x coordinate now becomes x plus h. Once again, the y coordinate of Q is found by substituting the x coordinate, x plus h, into the function. So the y coordinate becomes f of x plus h. This means that the coordinates of Q are now known as x plus h and f of x plus h. Now let's consider the gradient of the secant. And we know that the gradient of any straight line is equal to the rise over the run. So first of all, let's have a look at the rise and the run here. We have the run here, which we know is equal to h. And we have the rise here, which is found by finding y2 minus y1. And of course the run is found using x2 minus x1. So we can see here we have y2 minus y1. So we have f of x plus h minus f of x. And x2 minus x1 becomes x plus h minus x. So this formula here is known as the gradient of the secant. This formula is simplified here on this line simply by simplifying the denominator. If we have a look at the numerator up here, we can see it looks no different to the previous formula. We have y2 minus y1, or f of x plus h minus f of x, but when we get to the denominator, we've collected like terms here to simplify. So we have x minus x, which will cancel each other out, and we're just left with h here in the middle. So the denominator simply becomes h. Now, if we look at this formula here, we know this is the gradient of the secant, but we want this formula to eventually derive a formula for the gradient of the tangent. If we look at the curve here and we look at the point Q, if I moved Q down the curve like so and moved it towards the point P, what would happen to the value of h? If we go back to point Q now, where h is this distance here, if I move it closer towards P, we can see that as I keep moving Q, h will actually get smaller. The value of h will get smaller and smaller until eventually, when I hit the point P here, h will be equal to 0. So therefore we say that as this value h here approaches 0, Q will get closer to P along the curve, and PQ, the secant, will then become the tangent to the curve at P. We can therefore say that the gradient of the tangent at P is equal to this formula here. Now this is the actual formula which is known as the first principles formula, and it basically gives us the gradient of the tangent will be equal to the gradient of the secant, f of x plus h minus f of x, the whole thing over h. The gradient of the secant when h approaches 0. So therefore the whole formula is known as the limit as h approaches 0 of the formula f of x plus h minus f of x over h. Of course, h cannot be equal to 0. We know if h was equal to 0 in this formula, it would make the whole formula undefined. F dash x denotes the gradient of the tangent. And we say that f dash x is the gradient function of the original function f of x. And the process of finding the gradient function using this method is known as differentiation from first principles. Now there are two different forms of notation that are commonly used to represent a function and its derivative or gradient. The first type of notation is known as European notation, and we sometimes call that Leibniz notation. This is where we use the notation y to stand for the original function, and therefore the derivative or gradient function is known as dy dx. And what this literally means is the derivative of y in terms of x. This notation is sometimes known as y notation, and it's named after the German mathematician Leibniz. Now the second type of notation we can use is known as function notation, where the original function is denoted as f of x. And when the original function is denoted as f of x, we call the gradient or derivative function f dash x. This is known as function notation as opposed to Leibniz notation or y notation. Now another way of looking at this is to show this diagram here. Once again, we have a blue curve here shown, which we'll call f of x, and we have 2 points on the curve, point A and point B, and we have a black line joining those 2 points, which is known as the secant. This red line down here is the tangent to the curve at point A. We can see here at the moment that the gradient of the secant is equal to 10.06, but the gradient of the tangent is equal to 6. If we look along here, along this horizontal line, we can see that here is the value of h, and we know that A is at point x is equal to 3, and B is at x is equal to 7. So the value of h is equal to 4 here. Okay? The rise of the secant will be from y is equal to 10 to y is equal to 50, so it'll be equal to 40. Hence we have a gradient here of approximately 10 for the secant and approximately 6 for the tangent. Now, if I move point B down the curve, you can see that the value of h is decreasing. Here's the value of h here. Okay? We can see that h is being calculated and it's now down to 2.46. If I continue to move the point B, we can see that h continues to get smaller. And we can also see that the black secant, as I move B, is getting closer and closer to point. Sorry about that, guys. Had a bit of a technical difficulty there. But as you can see, if I continue to move the point B towards the point A, I can see h continuing to get smaller and smaller. And as it does so, we can now see when A is sitting on B, or B is sitting on A, the secant is now sitting on the tangent. And we can see the value of h here very, very close to 0. It's actually at 0.01, but this is only because of the technology that I'm using here that won't actually get me exactly to 0. But you can see that if this point, if B was sitting perfectly on point A, that h would be equal to 0. I move B away again from point A, and you can see the value of h increasing and the black secant and its gradient increasing all the time. So this really demonstrates as the way in which as we move B towards point A, the value of h decreases and gets closer and closer to 0. When h is actually equal to 0, B is sitting on A, and the gradient of the secant becomes the gradient of the tangent. Now the process of finding the gradient function using this formula here, the limit as h approaches 0 of f of x plus h minus f of x, the whole thing divided by h, is known as the first principles formula, and it's called differentiation from first principles. Now this is a different formula to the differentiation rule, which we used a couple of lessons ago, and that rule is much simpler than this one. But differentiation from first principles really does show you how the gradient of the secant and the gradient of the tangent are related. This formula is always used if a question asks you to differentiate using first principles. The second part of this tutorial is coming up, where we look at a couple of examples and how to differentiate using first principles. I hope you found it helpful.